if you're watching this video, I'm guessing you missed out on our class discussion today. So let me kind of recap what we had talked about. And I kind of hurried us along just as a review. Remember, if I give you this function right here, you can find the derivative by taking the limit as h approaches 0 and using our difference quotient. Okay, I've done several steps worth. You can see this is a pretty hairy function to be working with. So it took a few steps. I've crossed things off. Then I wrote what was left. Everything that was left had an h, so I divided everything by h, and here I am. Once I got rid of that h, now I'm able to do my direct substitution. So I'm going to plug 0 in for all of the h's to see what my derivative is. I'm going to end up with a 15x squared. The next term's going to go away. The 5h squared goes away, minus 6x. The 3h is going away, plus 7. That's the derivative right there. Now, I did all the hard work for you, so that seemed pretty simple, huh? Well, what we're going to look at today, you're probably going to hate me. Man, we're going to look at something here today. We're going to look at what we call the power rule, and it's kind of a shortcut to doing all of this. You're going to love me, not hate me. You're going to love me because I am going to share an awesome little rule with you. If you were to take a peek at our original function, and our goal is to maybe be able to get from there straight down to the derivative by using what we call the power rule. I want you to take a peek right here at this first term. And the power was a 3. And the coefficient was a 5. Where do you suppose this 15 comes from? Let's check it on the others. Power is a 2. Coefficient is negative 3. Look what we got, a negative 6. This term, the exponent was a 1. Coefficient is a 7. Okay, hopefully you're catching on. Just take the exponent times the coefficient and you have your new coefficient. Exponent times the coefficient, new coefficient. But the other thing we have to look at is what's going on with the powers, because see how this was x cubed? It's not x cubed, it's now x squared. This was an x squared, now it's just an x to the first. This was just an x to the first, now the x is totally gone, which would be like an x to the 0 power, which we don't write because that's just 1. What happens is that this exponent right here goes down by 1 unit. All right, so one more time. Do you think then you could go from here to here without all of that fun stuff? Well, think about it. 3 times the 5 is 15. Drop the power by 1. 2 times negative 3 is negative 6. Drop the power by 1. Okay, so now a couple details. So this one is an x to the first power, so that multiplies by 7, but then you end up with an x to the 0, which we don't write. And the other thing to comment on is this is a 4x to the 0 right now. And that's why when you take 0 times 4, there's no term out here. If you just have a constant, it's going to disappear when you go write the derivative. Let's go ahead and practice this power rule. Now the power rule works really good when you have polynomials that have lots of powers. So all those problems where we were doing Pascal's triangle, those are the ones this is nice for. Now the power rule is not always going to work, but there are some times that it is going to be helpful. Here we go. Take the coefficient times the exponent, and that's going to get you 6. Drop the exponent by 1. It's now an x squared. Take the exponent times the coefficient. Drop the exponent by 1. The exponent is assumed to be a 1 times negative 5. Drop the exponent by 1, which is going to be an x to the 0, and it's going to be gone. And this is already an x to the 0, so when you multiply the power, you're going to end up with a 0, and it goes away. There's the derivative right there. Not having to do it as a limit, just using the power rule. Let's try one more time. Take the exponent times the coefficient. Going to get you a 16. Drop the exponent by 1. And then you have this 2 that is a constant. It's like that x to the 0. That's just totally going to go away. I'm done. Right there's my derivative. Okay, this is pretty slick, and we are going to use this every chance we get. Now, like I said, it doesn't always work. So on your test, you will still have some problems where you're going to have to do the difference quotient, and there are going to be some problems where you get to use the power rule to find the derivative. Now, it obviously works great on this nice polynomial function. It can also sort of work on some other, even if the exponents are weird. Let's look at what I mean. Here I have this weird function that I've written with a variety of different types of issues. This one has a negative exponent. This one has the variable in the denominator. This one has the variable caught up in a square root. All of those, though, we could write somehow with an exponent. The first one, I'm just going to leave it. I'll deal with that -3 exponent here in a second. On this next problem, when you have an exponent in the denominator, it's down there because of a negative exponent that shot it down there. So I would have a 3x to the -4th, and that's how I would write this instead of writing it as a fraction. Plus 7x to the, well, when you square root, what kind of power is that? It's a 1/2 power. Okay, so let's go find the derivative now. The derivative of this function. I'm going to take my exponent times my coefficient and get -15 x to the, now this might be weird. I say drop the exponent by 1, but what I mean is I'm going to subtract 1. What's -3 minus 1? It's -4. Let's look at this next term. I'm going to take my exponent, which is a -4, times my -3. That's going to end up being a +12. X to the, and again, I'm going to subtract 1 from my exponent and get a -5. Plus, okay, now this next one, I could have made my life easier. Not sure why I chose a 7, but I did, because I'm going to take 1/2 times 7, which isn't beautiful, but I can just write it as 7/2. Now, x to the 1/2. Now I have to drop my exponent by 1. So what's 1/2 minus 1? Well, that's -1/2. All right, now we rarely leave negative exponents in our answers. So we're going to come back, and everything that has that negative exponent, we're going to shift it to the denominator. This first term is going to look like a -15 over x to the 4th plus 12 over x to the 5th, and then this whole, oh, you know what, did you catch that I missed my 7/2? It's x to the -1/2. So what's going to happen with that is my 7/2 is my fraction, and the x to the -1/2, the fact that the x has the negative exponent, it's going to go to the denominator, and rather than writing it as a 1/2 power, I'd probably go back and leave it as a radical. Sometimes we take the time to go ahead and rationalize that. Sometimes we don't. I'm not going to today. We're going to leave it like that. Even if you have some weird exponents, you can still use your power rule. I'm going to go through some of the problems that you're going to have on your homework. Now, you're going to do some finding the derivative, and you're going to be practicing doing the power rule today. That means that anytime they ask us to do anything with the derivative, we're going to use the power rule rather than going back and doing the difference quotient. We're practicing the power rule today. Let's look at number 8 here on your homework. It says, find the slope of the line tangent to the graph of the function at the given point. All right, this is just like our old homework was in our it was like the first lesson when we first learned the derivative. And we we're doing the difference quotient, but we were doing it at a specific point. So on this one, I'm going to start off and I'm going to find the derivative. The derivative of my function using the power rule. I'm going to take 2 times 1/2, that's just a 1, x, and I subtract 1 from the exponent, so it's just an x. Okay, plus 12, any constants just go away. The derivative of my function is just x. Now, if I want it at a given point, that means I'm going to take this x value and see what is the slope at that particular x value. So I'm finding the derivative at x equals -3. Well, plug -3 into the function and you just get -3. We're done. The y value that they gave this is just a different way to do this. At some point, sometimes they just said at x equals -3. On this one, they actually gave me the full ordered pair, but I didn't really need to use the y for anything until I do this one. It says find the equation of the line tangent to the graph of the function at the given point. Okay, got it. I'm going to do the same thing I just did. But they also want me to write the equation in slope-intercept form. That misspelled that, sorry. In slope-intercept form. That's where I'm going to need that y value. Let's start off and find the derivative using the power rule. Take your exponent times your leading coefficient, or times your coefficient. That's going to be a -2. X to the, now it's going to be to the first power. On your next one, it's assumed to be a 1 there. That means when I take it times my coefficient, I'm going to have a -1. And then it's going to be, I kind of need to write that -1 because it's going to be an x to the 0 when I subtract that. And we don't write x to the 0. That means I just have -1. That's my derivative. Now I'm going to find the derivative at a particular spot. Not the derivative of x, but the derivative of 0.5. That means I'm going to plug 0.5 in for x. -2 times 0.5 is -1 minus 1. That's going to equal -2. Now remember that when you find the derivative, what you're finding is the slope of the tangent line. I just found the slope of my tangent line to be -2. I also have an ordered pair. And if I have the ordered pair and I have the slope, I can write the equation of the line. Now, personal preference, you might use slope-intercept form and go solve for b. That's okay. I'm going to use point-slope form and write it that way. Let's plug in everything we can. So it's going to be y minus y1, so y minus 1.25 equals my slope, -2, times x minus 0.5. And then I'm going to do a couple things. I'm going to distribute here. And I'm going to add my 1.25 to the other side. Looks like my equation is y equals -2x plus 2.25. That is the equation of the tangent line to this function at that spot. Last example. This says find the derivative of each function. Recall that this is the slope of the tangent line. Yep. Find the coordinates of the point at which the slope of the tangent line equals the designated slope. So in this particular example, we want the designated slope to be 0. All right, we're going to go ahead and start off, and let's just go use our power rule to find the derivative. Exponent times coefficient. X is now to the squared. Exponent times coefficient, and then x is now to the 0, so it's not there. This is the derivative. Now rather than saying, notice it doesn't say x equals 0, what they want is the slope to be 0. Remember that the derivative is the slope. So we're trying to figure out what x value here could we plug in. At what point on this graph would the slope of my tangent line be 0? Now this leads us into something that we're going to be doing later on tomorrow, and that's why they're having us try this. Let's set this function right here equal to 0. Let's see when the slope is equal to 0. 9x squared minus 36 equals 0. Different ways to solve this. I'll go ahead and add the 36 and divide by the 9. And then I'm going to take the square root of both sides. And you got to be careful here, because when you square root this, don't forget that plus or minus. That means the slope of my tangent line here is going to be 0 at two different places. It's going to happen at 2, but it's also going to happen at x equals -2. The directions say find the coordinates of the point or points at which the slope of the tangent line equals 0 in this case. That means I know one of my points is going to be 2 something, and one of my points is going to be -2 something. I have to find the coordinates. I've got to find the y value that matches each one of these x's. You always, when you're trying to find your y value, you always go back to the original function. You're going to plug 2 in right here and put 2 in here, and let's see what we get. 2 cubed is 8 times 3, that's 24. And then I'm going to plug 2 in for the x, so that's going to end up minus 72. 24 minus 72. It's going to give us a 48 for the y value when x is 2. Let's try again with -2. -2 cubed is going to be a -8 times 3 is -24. And then I put -2 in for x. That's going to make that a positive 72. When you combine those two like terms, you're going to end up this time with a positive, with a positive 48. All right, so that's a nice little summary of the different types of problem that you're going to have on your homework. Today, anytime you're doing the derivative, you get to use the power rule. Go enjoy.